All right. Hi, everyone. Welcome to another lecture of Nets 412. So today I want to continue our thinking about how to maximize revenue in auctions by making fewer and fewer assumptions. So just to recap, remember originally we thought about auctions in Bayesian settings. So we both had everybody up front and we knew the distribution from which they were drawn. And we were able to design auctions that maximized revenue amongst all possible truthful auctions. And when we said revenue, since we had a distribution in mind, we talked about maximizing expected revenue. And there was an exactly optimal auction because we had this well-defined benchmark. And then we thought to ourselves, okay, well, that's great, but we don't always get to run auctions because it's hard to gather everyone who might be interested in the item together at once. And so sometimes we like to just price things. And again, in this Bayesian setting where we knew the distribution from which people were drawn, we figured out how to come up with pricing schemes, simple pricing schemes that would achieve within a factor of 2 of the profit that we could obtain from the optimal auction if we did have everybody up front. Okay. And then last lecture, we thought to ourselves, well, that's great, but where does this distribution come from? Like why should we imagine that people have their valuations drawn independently from some distribution? And even more than that, why should we imagine that we know exactly what this distribution is? Because when we designed these Bayesian optimal auctions, we really needed to know the details of this distribution in order to set the auction rules, to set things like reserve prices or the fixed prices we were going to be charging. And so last lecture, we figured out a way to think about this in a prior free setting without needing to assume that buyers were drawn from distributions, let alone that we knew what those distributions were. And we gave this random sampling auction, and we showed that it achieved some factor, a factor of 4, of the optimal revenue that could be obtained by a fixed price, instance by instance. And we sort of observed that this fixed price benchmark was a sensible one because if people had been drawn from distributions and if we had known what those distributions were, the Bayesian optimal auction would have corresponded to setting some fixed price, the monopoly price. Okay. And so in this lecture, I want to continue imagining that we're in this worst case setting. We're still going to think about digital goods auctions because it's been a good test bed for developing these techniques. I'm going to still imagine that we're in these worst case settings. We have no idea where these bidder valuations are coming from, and we certainly don't know a distribution from which they're coming, even if they are coming from some distribution. And now I want to ask the obvious next question. Okay, we thought about how to deal with this when we had everyone up front, how to run an auction, this random sampling auction. But now I want to be more ambitious. I want to still work in this sort of worst case setting, but I want to think about how to maximize revenue when I have to stick with pricings, when I have to allocate items as buyers arrive one at a time without needing to have everyone up front. And so the model that we're going to think about today is exactly that. So there's going to be some number of buyers N, but they're not going to all be up front they're not going to all be up front. So it doesn't make sense to run an auction. Instead, buyers will arrive one at a time. Their valuations don't necessarily come from a distribution. In fact, their valuations can be chosen adaptively by an adversary as a function of what we've done so far. And I'd like to think about how to sell to them in this online setting so that we can still compete with this fixed price benchmark. And We're going to solve this problem using a tool that we all know and love and is going to bring the class full circle, but maybe that you haven't thought about in a little while. And we're going to solve this problem using the polynomial weights algorithm that we introduced early on in the course to think about learning dynamics and convergence to equilibrium. Okay, the polynomial weights algorithm turns out to be a very powerful learning algorithm, and we're going to be able to squeeze, a little bit more juice out of it this class as well. Okay, so let's think at a high level about what we want to do, and I'll briefly recall what we did last lecture when we derived the random sampling auction. So what did the random sampling auction do? So it randomly split the bidders into two buckets, and within each bucket we solved some estimation problem. We computed the optimal revenue in that bucket, and then we used that statistical information that we learned from bucket one to design the auction that we were running in bucket two, and vice versa. Right? We had to estimate something on bucket one and use that information in our bucket two auction, and vice versa, because we didn't want the prices, we didn't want the pricing rule in our auction to depend in any way on the reported valuations of the particular bidders, because that wouldn't have yielded a truthful auction. Okay, so we can't do that, right? Like, we can't run this random sampling auction, because to do that, we sort of inherently need everyone there at the same time. We need to look at everyone's valuation in a certain bucket, and we need to estimate what the optimal profit achievable on that bucket would be. But at a high level, we can still try to do something similar, right? Like, what were we trying to do? We sort of, by deriving these revenue, these profit extractors last time, what we did is we reduced the auction problem, the auction design problem we were trying to solve, to a learning problem, to some statistical estimation or learning problem, which corresponded to figuring out, based on data, what the optimal achievable revenue would be, and then using that information to run our auction. And so we're going to try to do the same thing. Okay, we're going to try to reduce the problem of running an online auction that is nearly revenue maximal to some learning problem, to some statistical estimation problem, except now we have to reduce it to an online learning problem. We have to reduce it to a learning problem in some setting in which the algorithm is dynamically interacting with some environment and somehow learning as it goes along. Okay, which is exactly the setting in which we already derived the polynomial weights algorithm. And that's why it's going to be a useful tool for us. Okay, so our goal is to find a truthful online auction to approximate the optimal revenue. And let me tell you what an online auction is, because it's going to be a little bit different than just a pricing scheme. You can use these ideas to develop a pricing scheme as well, and we'll do that next lecture, but it's a little bit easier to design the online auction. So here's how an online auction works, and this is how it sort of differs from just a pricing scheme. So bidders still arrive online. They arrive one at a time. Okay, so bidders arrive sequentially, but rather than just facing a price, we're still in a setting where they're going to report their valuation, and we're going to try to incentivize them to report their valuation truthfully. Okay, but it's a sequential online auction, because the constraint that we have is that, when bidder I arrives, we get to look at his valuation, but then we have to decide on his allocation and payment rule before the next bidder arrives. So we have to make allocation and payment decisions for bidders one at a time before we have the luxury of knowing who's going to come next. Okay, that's sort of where the difficulty arises. And we still want to design our allocation and payment rules to incentivize bidders to report their valuations truthfully. Okay, so what we're going to do is going to sort of, you'll see it's going to look a lot like a pricing scheme in that at the auctions we develop, we'll sort of decide on a price ahead of time. It'll say, okay, like, the price today is $16, but we won't just, put a price tag on the item. Instead, we will ask buyers to report their valuation, and then we will decide if their reported valuation was bigger than the price we decided on, bigger than $16 or not, and implement the allocation rule that way. So this is definitely less natural than a pricing scheme. Like, typically we do dynamic pricing all the time, but we don't typically run online auctions like this. You should think about this as sort of a stepping stone towards coming up with a true dynamic pricing scheme. And in fact, very similar ideas can give a real pricing scheme. It's just a little bit more complicated. So we're going to derive an online auction today, just because doing so involves solving a lot of the same learning and statistical estimation tasks with a little bit less complication. But in fact, we will see, using a similar idea, how to actually derive like a real honest to goodness pricing scheme next lecture. Okay, and just to sort of recall our benchmark, we want to compete with the best fixed price in hindsight, right? So if we charge some price P, then the amount of money we make is, well, P, because we get P dollars every time someone buys an item, times the number of people who are willing to buy at that price. And as we observed last class, at least in hindsight, after I see the valuations of all of the buyers, the best fixed price in hindsight is always equal to the valuation of one of the buyers. Right? We argued this last time, because at least given the particular realization of buyers' valuations, if the price that I used fell strictly between the valuations of two buyers, I could like wiggle my price up just a little bit without changing the number of people who were willing to buy at that price, but increasing the amount of money they would pay me when they buy. And so anything that allows me to do that couldn't possibly have been the optimal price in hindsight. Okay, and that means that we can write our benchmark a little bit more simply. It's the maximum over all possible choices of j times the value of the jth highest bidder. That's just because if we set our price to be the value of the jth highest bidder, then there will be exactly j people willing to buy the item. And we defined this sort of slightly relaxed benchmark, right? Which we called sort of opt greater than or equal to k for fixed values of k. And that just corresponded to the revenue of the best fixed price that sold to at least k people. So just to remember what we did last time, we were able to compete with this benchmark for k equals to 2. And what we proved is that the random sampling auction achieves at least a quarter of the revenue, achieves a 4 approximation to the benchmark of the best fixed price that sells to at least 2 people. And so, well, we'll see exactly what our guarantee is going to be at the end of the lecture. It's not quite this, but we're, in addition to wanting to solve this harder online version of the problem, in this class, I want to do better than a 4 approximation. I want to really sort of approximate to the revenue of the best fixed price almost exactly. So I want to aim for something that looks more like a 1 plus epsilon approximation, where I'd like to make epsilon as small as I want. Now, of course, we already saw that in general, that's impossible. For example, if the best fixed price sells to only one person. And so what we're going to do is we're going to give some guarantee that corresponds to a 1 plus epsilon approximation to our fixed price revenue benchmark, essentially in the situation in which we end up selling to lots of people, where our revenue comes, where our revenue should sort of come from a number of bidders that grows with the total number of bidders n. Okay. So are there any questions? So this is sort of all so far recap and motivation for the kind of thing we want to do. And I'm going to jump into definitions now, but this is a good time to ask questions if there's sort of confusion just about, either what we did last class or, for the last 3 or 4 classes, or about why we're doing what we propose to do. Okay. So let's just define the setting in which we're going to be working, which I'll call an online digital goods auction. So we're going to have n bidders, and each of these bidders will have some valuation for the good. By the way, remember that a digital goods auction is just an unlimited supply auction. Our set of feasible alternatives are all possible subsets of bidders. It's a setting where we have 0 marginal cost of production, and think about selling software, and so there's really no supply constraint. We can sell the item to whoever we want to. Our only constraint is revenue. So we've got n of these bidders, and they've each got valuations, which we're going to normalize in this class to lie between 0 and 1, which is just how happy they're going to be if they're chosen to be a winner. If they're chosen not to be a winner, then they'll get $0. And well, it is an auction setting, but it's an online auction setting. So there's a time element. At time t, bidder t arrives. We make no assumptions at all about where bidder t's valuation comes from. It could be, again, chosen by an arbitrary adversary. And he reports, well, something, right? He could lie, but we're going to try to design dominant strategy truthful mechanisms that will incentivize him to report his true valuation. And then the item is either allocated or not, and he's asked to pay something. But the crucial difference between an online auction and a offline auction is that the allocation decision that we make at time t and the payment decision that we make at time t, right, like whether we give him the item and how much we charge him, can only be a function of what we've seen in the past, not what we've seen in the future. Right, so when we defined allocation and payment rules in the standard like offline auction setting, the allocation and payment rules were a function of the reported valuations of all n of the bidders. But here, for bidder t, the allocation and payment rules can only be a function of the valuations of the bidders that came before t, plus, of course, bidder t's reported valuation. Okay, so in particular, for t equals 1, like if you're the first person who arrives, then whether you get the item is a function only of your own bid. If you're the second person, whether you get the item and how much you're asked to pay can be a function of both your own bid and the bid of whoever came yesterday. So we're allowed to learn, we're allowed to adapt as we go on, which of course we must, because at the beginning, at round 1, we know absolutely nothing about the instance that we're facing. So we're definitely going to have to make use of historical information if we're going to want to try to make correct decisions as we go along. But the point here is that, mathematically, these allocation and payment rules cannot depend on information that the auction doesn't have yet, namely the reported bidder valuations for bidders who haven't yet shown up. Okay, so this is sort of an obvious thing if you're thinking about designing an auction that has to make these sequential decisions. But mathematically, this is what distinguishes an online auction from an offline auction, that the bidders have sort of times associated with them, and the allocation and payment rules corresponding to the bidder who shows up at time t can only depend on the reported valuations of bidders who showed up on days 1 through t, and not on day t plus 1. Okay, makes sense. Okay, and it can be daunting to try to think about allocation and payment rules in the abstract. Like in principle, there could be really a lot of different kinds of allocation and payment rules. it's going to be helpful for us to think about a particularly simple kind of allocation and payment rule, although if you think about it, this is really the only thing you can do if you want to have a deterministic auction that is dominant strategy truthful. Okay, so we're going to focus on a particularly simple kind of allocation and payment rule that really sort of corresponds to a pricing scheme, and it's called a take it or leave it auction. And the idea is pretty simple. Basically, at any given moment, we're going to have a fixed price in mind. Like, it's really, under the hood, this is really a pricing scheme, right? So I will decide based on the bidders I've seen so far that, like, today, I'm going to try to sell the good for $16, and the only way the good can sell is if you pay me $16, and I'm not going to ask for more than $16 no matter what happens. Okay, but like we're going to think about this in an auction setting, so we're still going to think about an allocation and payment rule as opposed to just a price, but it's really a pricing scheme. So at time t, under the hood, there will be some fixed price that is computed. Let's call that st. Okay? And this fixed price, whatever it is, will be some function of the bids that have been reported by bidders 1 through t-1. So the bidders that have shown up strictly before bidder t. In particular, this is the price we're offering to bidder t. It is going to be entirely independent of his own bid. Okay, so the price that we use at day 1 is just a constant. Like, it's not a function of anything because we haven't seen anything yet. Now, as a function of what happens at day 1, I can decide what my price at day 2 is going to be. Okay? And then as a function of what happens at day 1 and day 2, I can decide on what my price at day 3 is going to be, so on and so forth. But again, I can't look into the future, and I'm not going to try to set the price as a function of today's bid. And then the allocation and payment rules will correspond to whether the bidder, given their reported valuation, would have been willing to buy the item at this fixed price st. Okay, so they're extremely simple. The allocation rule just says we will give the item to bidder t exactly when his reported valuation is above the fixed price. And if we give the item to him, we will charge him exactly the fixed price. Okay, so this is what I mean by under the hood, this is really just a fixed pricing, right? Like, if I had put a price tag of st on this item, then what I would find is bidder t would buy the item if his valuation was above st, and otherwise he won't. That's exactly the allocation and payment rule I'm going to use. The only reason we're thinking of it as an auction is because it will be convenient for us to have the bidder actually report his valuation. Okay, that'll give us more information that'll make the learning process a little bit easier to think about. Okay, and the key thing here is that the item is sold at a fixed price to bidders with valuation above that price, and the price is computed independently of a bidder's own bid. Okay, so under the hood, it's just a pricing scheme. Okay, and so I want to make a couple of simple observations. So first of all, even though under the hood this is behaving just as a pricing scheme, we are going to make use of the fact that the bidders are actually, not just giving us this binary feedback of whether they buy the item or not. Like, the bidders are actually reporting to us their valuations. And so it's going to be important that the take it or leave it auction, this auction format that we're going to run, actually is dominant strategy truthful. That, if we're going to ask people to report their valuations, well, and especially if we're going to use that for learning, then we should incentivize them to report the truth, right? For the same reasons, we always want to incentivize truth-telling, that if we're not incentivizing truth-telling, we have no reason to believe that the reported valuations correspond to the real valuations, and therefore anything we learn from the reported valuations might not actually be true about the real valuations. But fortunately, it's sort of immediate that these take it or leave it auctions are dominant strategy truthful exactly because they look like pricings. Okay, So the key point here is that this price that we came up with, this price under the hood, ST, that determines the allocation and pricing rule for bidder T, was computed independently of his own bid. So it's not like by over-reporting his valuation or by under-reporting his valuation, he can change the price that he's facing, right? The only thing he can do, like say his valuation is above the price, right? So if he reports truthfully, he gets the item at a price that he's willing to pay because his valuation is above the price. If he misreports upwards, if he reports something larger than his valuation, then he still gets the item, right? Because his reported valuation is still above the price, and he doesn't have to pay any less because we always ask him to pay the price if he gets the item. The payment is independent of his own bid if he gets the item. And by shading his bid downwards, the only thing he can do, the only thing he can change is he can cause himself to lose the item. If he, misreports his valuation to be something that's below this price, he'll lose the item. Similarly, right, if your valuation is, below the price, then reporting downwards doesn't help you. And reporting upwards, the only difference it can make is it can cause you to win the item at the price, which after all, you weren't willing to pay. Okay, so like basically what's going on, what makes this truthful is that secretly we've come up with a fixed price. And, it's like an auction, so I haven't told you what the fixed price is, but somehow I've promised to act in your best interest and just charge you the price if your valuation is above the price and, not sell you the item if your valuation is below the price. Since I'm acting exactly as you would if you got to see the price, then it is of course in your best interest to tell me your valuation. Okay, so that's the idea. So it's a very simple form of truthful auction. And actually, if you think about it, it's really without loss of generality. Like any sensible auction in this online auction setting actually sort of has this form. And it's not too hard to see why. Right, so this is a single parameter domain. So we know that any truthful auction must be monotone, meaning your probability of winning the item can only go up if you report a higher valuation. Okay, so we could have various exotic randomized allocation rules that would not really correspond to fixed pricings, but if we want to run a deterministic auction, right? If we're running a deterministic auction, then what it means in a single item auction that you have a monotone allocation rule is that, as you raise your bid, you can't go from winning to losing. So all that can happen is that at some point, that's when you cross some threshold, you go from losing to winning. Okay, so for any truthful deterministic auction in this kind of single parameter setting, there will just be like a threshold allocation rule. If you bid above some threshold ST, you win the item. If you bid below the threshold ST, you don't win the item. And then if you think about what kind of payment rule is needed to make that truthful, well, I had better charge you ST. I had better charge you the cheapest price that you could have bid to still win the auction. Otherwise, you would have wanted to bid that. And indeed, if you go back and look at our payment rule for monotone allocation rules, you will find that the payment rule indeed has to charge exactly this threshold ST. Okay, so at least if we restrict ourselves to auctions that are sort of deterministic at the end, the payment scheme has to look like this kind of pricing. So basically, it is essentially without loss of generality to look at these take it or leave it auctions, even though they're pretty simple. All right, so we have an auction format, and it sort of has this simple functional form, right? Like basically, if we're going to run a take it or leave it auction at every round, then the only thing we need to figure out is what price we're going to charge. Like, what is ST exactly? So every day we need to come up with some price ST to charge. And the premise, of course, is that we're going to try to learn this best. We're going to try to learn the right price to set as we go along. Initially, we don't know anything at all about the instance. We have no idea what price to fix. But as we start running our auction, as the bidders arrive, we learn more and more about what their bids look like, and we'd like to do some learning. And so the high-level idea is to use the polynomial weights algorithm with prices as experts. Okay, so let's remember what the polynomial weights algorithm was. We studied it quite a bit, but it's been a little while, so let's just remember the setting in which it works. So we derived the polynomial weights algorithm in this abstract setting where we had a collection of different experts, okay? And these experts were entirely abstract, but what would happen is every day we would need to choose an expert, and then something would happen. The experts would experience some gain. When we first derived the polynomial weights algorithm, we talked about losses instead of gains, but it's entirely symmetric, so we can talk about gains as well. Okay, so at round one, like step one of a round, we choose an expert. Then all of the experts experience some gain, some payoff, okay, which is some number normalized between 0 and 1. And we, as the algorithm, experience the gain of the expert that we chose. Okay, and there's no distributional assumptions at all, right? That was sort of the beauty and the power of the polynomial weights algorithm and what allowed us to play it in adversarial games. We didn't assume anything at all about where these gains came from, right? They could really be chosen by an adversary who was trying to ruin the guarantees of our algorithm. And what the polynomial weights algorithm promised was that for an arbitrary collection of n experts, okay, and for an arbitrary, possibly worst case sequence of losses, it would always be able to make choices so that its regret to the best expert in hindsight was small. Okay, it was able to make choices so that the payoff, the cumulative gain of the algorithm was nearly as good as the cumulative gain of the best expert in hindsight, right? Whichever expert in hindsight turned out to do the best. Of course, the algorithm doesn't have the benefit of hindsight, which is what makes this guarantee remarkable and powerful, right? But it's saying if like no matter what happens, we can figure out cumulatively how well each of the k experts did. Okay. In particular, we can compute the cumulative gain of the best expert, the maximum gain over all of these experts in hindsight, because we're looking at the cumulative gain after t days, after we've seen all of the rewards. And the cumulative gain of the algorithm was guaranteed to be at least the cumulative gain of the best expert, minus some term that grew sublinearly in t, that sort of, this error term here grew only with the square root of the number of rounds times the log of the number of experts. Okay, and this was a good bound because you'd sort of expect that since these are cumulative losses, you'd sort of expect that cumulative losses over t days would tend to grow at a rate that is linear in t, whereas our sort of fudge term here, our error, grows at a rate that is sublinear in t, only sort of the square root of t, and has a very, very mild dependence on the number of experts, just square root the log of the number of experts. And so this should become, in natural settings, sort of a low order term compared to the cumulative gain, which should be growing, something like linearly in t. And so asymptotically, in fact, at a reasonably fast rate, the polynomial weights algorithm was guaranteed to really do as well as the best expert in hindsight. Okay, so this was the sort of power tool that we derived at the beginning of class. The idea is going to be somehow to use this power tool to try to learn prices to use in this sequence of take it or leave it auctions. And the idea is going to be to identify prices as experts. Okay, the experts in the polynomial weights algorithm will correspond to prices we could have used, and we want to set things up so that the gain of the best price in hindsight corresponds to the revenue of the best price in hindsight, the best fixed price. And if we can rig things up so that this guarantee ends up telling us that our revenue is nearly as good as the revenue of the best price in hindsight, we will have solved our problem. Okay, does that make sense? It's actually not going to be so hard to do this once we've set it up. So are there questions about the basic agenda and why it makes sense to try to use the polynomial weights algorithm in this setting? Okay. So we do have one complication, which is that we would like to compete with the best fixed price out of all possible prices. Now, we don't really need to consider all possible prices because remember, we've normalized valuations to be numbers between 0 and 1, so we don't have to consider prices that are bigger than 1. Nobody will be willing to buy at prices that are bigger than 1, but still there's a lot of numbers between 0 and 1. There's continuously many, and the polynomial weights algorithm can't, at least as we've derived it, handle infinitely many experts. It only handles a finite discrete number of experts. So right off the bat, we're going to need to make some choice. We're going to need to select some finite subset of the prices and use those as our experts, and somehow hope that that'll allow us to still be competitive with all of the infinitely many prices that we didn't choose. And then once we fix the prices that are going to stand in for our experts, we need to design what the feedback of what the feedback's going to be to the polynomial weights algorithm. Because after all, in the setting in which the polynomial weights algorithm works, every day the polynomial weights algorithm is going to choose one of these experts, but then it's got to learn in order to update for the next round. It's got to learn what was the gain or reward for each of the experts, not just the one that it chose. And so, of course, we want to identify somehow gains with the revenue that we make, because we want to turn the guarantee of the polynomial weights algorithm into a guarantee on our revenue. And so let's think about what the revenue would be, given like a fixed, given a valuation VT, okay, for the tth bidder, what our revenue would be at day t if we ended up charging some price S, if we chose some price S. Okay, and that's sort of a pretty straightforward quantity, because there's two choices here, right? There's two cases. Either the price that we chose, S, was less than the reported valuation. That's sort of the good case, right? If the price we chose was less than the reported valuation, that means, well, the valuation was bigger than the price, or in other words, the buyer was willing to buy the item at price S. Okay, in that case, we make S dollars. On the other hand, it might be that we chose a price that was too high. Maybe the buyer valuation was less than the price, in which case the buyer is not willing to buy the item and we make $0. So there's sort of this discontinuity at the valuation, right? Like our rewards sort of smoothly and continuously go up as we raise the price until all of a sudden we cross the threshold at which the buyer is willing to buy at that price, at which point our rewards sort of instantly and precipitously drop down to 0. But it makes sense to use these as our gains, right? So first of all, the scale is right. Like these valuations are normalized to be between 0 and 1, and so the prices we're considering are numbers between 0 and 1, and so these rewards, which are either the price we chose or 0, are numbers between 0 and 1. So these are numbers already on the right scale that the polynomial weights algorithm is prepared to receive. And the only other thing we need to make sure of is that we can actually compute these gains for every single expert, because that's what the polynomial weights algorithm needs. It needs to learn at every round what the gains were for each of its experts. And this is where it's going to be convenient for us to be running an online auction as opposed to a pricing scheme, right? Like if we just set a fixed price, if we put a price tag S on the item, then we would learn the reward for the price that we picked, right? Because we would observe whether the item was bought or not. And so we would see whether the reward for the price that we picked, the expert that we chose, was S or 0. But that feedback, whether the bidder bought the item or not, would not be enough for us to compute the gains for the other experts, for other prices, right? If we just learned whether the item was purchased or not, we wouldn't be able to compute the counterfactual for how much profit, how much revenue we would have made at some other price S had we used price S. We'd be able to figure that out for some prices S. For example, if I charge $10 and the item sells, right, so my revenue was $10, I can figure out that if I charge $9, my revenue would have been $9. And if I charge $8, my revenue would have been $8, because I know that the buyer would still have been willing to buy the item at a lower price. I would have just made the lower price as my revenue. But I don't know what my revenue would have been had I charged $11, right? There's two possibilities. The revenue could have been $11 or it could have been 0. Okay, similarly, if I set a price of $10 and the item doesn't sell, then I know what revenue I would have gotten at any higher price. I would have gotten $0 as well, but I don't know what revenue I would get at lower prices. Okay, and basically, like, this is the problem. This is the complication that you need to solve in order to come up with a true dynamic pricing scheme that we are just gonna sort of assume that we don't need to solve here, because in this lecture, we're just coming up with an online auction. This is why online auctions are going to be a little bit easier, have one fewer complication than dynamic pricing schemes. Because in an online auction, we don't just learn whether the item sold or not. We actually learn the bidder's reported valuation. And if I learn the bidder's reported valuation, I can compute all of these counterfactual gains. I can figure out how much money I would have made had I set the price to be $12, because now, even though I set the price to be $10, I learned that the bidder's valuation was $13. And so I know that had I set a price of $12, I would have gotten $12. Okay, does that make sense? So this is really where we're sort of taking advantage of the fact that we're running an online auction, that we're actually asking bidders to report their valuations, and we're incentivizing them to do it truthfully. It's so that we can have the feedback that we need to figure out what the gains would be, not just for the price we actually set, but for counterfactually other prices we could have set. And this is what the polynomial weights algorithm needs to run. There are algorithms that work in the same setting as the polynomial weights algorithm that don't need all that feedback, that only need the feedback of the, only need to learn the reward for the expert they chose. These are called banded algorithms. And we'll see an algorithm like this next lecture. And if you have an algorithm that can work in this limited feedback setting, which we do, they're just a little bit more complicated than the polynomial weights algorithm, then you can use exactly the same idea to derive an actual pricing scheme rather than an online auction. Because the only difference between a pricing scheme and an online auction is about the feedback that you get, about whether you can compute counterfactually how much money you would have made had you set the price differently. Okay, does that make sense? Any questions about that? Maybe that distinction will be a little bit clearer next lecture when we actually derive a dynamic pricing scheme. Okay. So how can we use the polynomial weights algorithm? So let's think about our benchmark. Okay, let's denote the revenue that we obtain using a fixed price P for the first T bidders. So this is how much money we could have made had for the first T bidders, for all of them, we offered the same fixed price P. Okay, and the revenue that we would have made is, of course, exactly P dollars, the amount of money we make every time we sell an item at a price of P, times the number of bidders up through time T who would have been willing to buy the item. Right, so our revenue of a fixed price P for the first T bidders is just P times the number of bidders who came up through time T, whose valuation was sufficiently large that they would have been willing to buy the item at this price P. So observe that because we have, observe that this is like just the sum of the revenue that we obtain at each of the days between 1 through T, right? Like, if our P of T is the revenue that we obtain at day T at some fixed price P, then this cumulative revenue, this is just the sum of the revenues that we could have obtained at days 1 through T, right? There's two cases. Either if today I saw someone whose valuation was below a price, it was below the price that I set, then this term would have contributed 0 to the sum. And if it was someone whose valuation was above the price, then this term RPT would have contributed P. Okay, so this is just the sum over all of the T days of these individual terms we defined on the last slide, which specify as a function of the price and the valuation how much revenue we make at that day. And because we defined the gains that we assigned to each of the experts in the polynomial weights algorithm to be exactly these per day revenue terms, then by construction, the cumulative gain of an expert corresponding to some price P, right, up through day T, is exactly equal to the cumulative revenue we would have obtained using some fixed price P to sell to the first T bidders. Okay, sort of just because we set things up this way, first of all, because we were able to decompose our cumulative revenue into a bunch of sort of atomic per day revenue terms, and second, because we were able to define the sort of individual day gains of the experts to be these individual day revenue terms, the cumulative gain of a particular expert identified with a price P is exactly equal to the cumulative revenue we could have obtained using a fixed price P. And so we can just sort of apply the guarantee of the polynomial weights algorithm to sort of observe the following fact. Okay, it's not quite what we want, but it's almost. And it's that if we use the polynomial weights algorithm every day to select a price from some finite set n, okay, and we feed back to it gains for each expert corresponding to the revenue that would have been made using the corresponding price. And then we use those prices every day as a take it or leave it, as the price in a take it or leave it mechanism. Then first of all, we have a dominant strategy truthful online auction. Like, first of all, we have designed an online auction as we defined it. That is, we have some mechanism that comes up with an allocation and payment rule every day using only information that's been available, up through day T. And second of all, it's actually a take it or leave it auction in the sense that we're just using information that we obtained on days 1 through T-1 to come up with a fixed price that we will use at day T. The particular way we're coming up with that fixed price is we are using the polynomial weights algorithm, which is maintaining some distribution over prices, which is a function only of the gains it's seen so far, which correspond to the bids of bidders 1 through T-1. Okay, and we know that take it or leave it mechanisms are dominant strategy truthful, so we have a dominant strategy truthful mechanism. And moreover, we know that the revenue that will be obtained by this mechanism is at least the revenue of the best fixed price. And here's where the caveat is: not the best fixed price out of all of the possible fixed prices between 0 and 1, but only the best fixed price amongst the set of prices n that we designated as experts. Okay, minus some error term that is just the polynomial weights error term, sort of corresponding to square root of the number of rounds we've run the auction for times log of the number of prices that we chose to use as experts. And so we have one remaining design choice, which is to figure out, okay, how should we choose this finite set of prices n? Right, because there's a trade-off here, right? Like on the one hand, if I choose a larger set of prices, then presumably this benchmark that the polynomial weights algorithm competes with, that is the revenue of the best fixed price contained within my finite set n, will get closer to the benchmark that I actually want to compete with, which is the best fixed price period out of all of the continuously many prices between 0 and 1, right? Like presumably the more prices I choose to compete with, the closer I am to competing with the set of all possible prices. On the other hand, there's a trade-off, right? Because this error term depends on the number of experts. And so the more prices that I choose, the larger this error term will be. Okay, and so somehow I need to balance these two things. And so let's think about like a simple parameterized discrete set of prices that I might choose. It's sort of a natural one. Okay, right, the prices I want to compete with are all of the possible prices between 0 and 1. Okay, so sensibly, it makes sense to try to like discretize that set, because the polynomial weights algorithm only has guarantees for finite numbers of experts, because its guarantees degrade with the log of the number of experts. If n went to infinity, this error term would go to infinity. And so why don't I choose just some like uniform discretization? So I'll choose some, like little number alpha less than 1, and I will just consider prices that are discrete multiples of alpha. So alpha, 2 alpha, 3 alpha, all the way up to 1. And there's no point including 0 in this set, because the revenue that I would obtain by pricing the item at 0 is always exactly 0. And so using a price of 0 is dominated by using any other price, right? Like in the worst case, if I use some higher price, I will also obtain 0 revenue. And there are some cases in which I obtain positive revenue. So there's no reason to include 0 in our discrete set of prices. And so there's two things we need to sort of understand about this set. The first is how big is it, because the size of this set comes into our error bounds. And then the other is, if I can promise you something about the revenue of the best fixed price in this set, what does that mean about the revenue of the best fixed price period? Okay. Yeah, and answering the first question is easy. Of course, if my prices correspond to multiples of alpha between 0 and 1, then the number of prices that I've picked is 1 over alpha, right? Like if my prices are 1/2 and 1, then the number of prices is 1 over 1/2. That's 2. If it's 1/3, 2/3, and 1, then it's 3. And in general, the size of this set is 1 over alpha. As a function of the discretization parameter, I choose alpha. Okay, and then here's the other thing we need to know. And this one's only a little bit more subtle. And so first of all, the claim is going to be that if I tell you that you are doing as well as the best fixed price in this discrete set n, then that is a promise in particular that you are doing as well as the best price in this continuous set between 0 and 1, minus possibly an error term that corresponds to alpha times n. And so let's think about why that is. Let's think about the sensitivity of our profit to small changes in the price. Okay, and it depends on whether you move the price upwards or downwards. So let's suppose that the best fixed price is P. Okay, the best fixed price period is P. I cannot say, right, and it's because it's not true in general, that every price that is numerically close to P will have revenue that is close to the revenue I would get of using P. Right, in particular, right, like it might be that lots and lots of people buy the item at price P because there are many people whose valuation is exactly P. And so if I raised the price to P plus epsilon for any positive epsilon, my revenue might like precipitously drop, because it might be that, you know, this is like just the threshold at which almost all of my customers find it no longer worthwhile to buy the item. Right? So, you know, there's like no guarantee that even if P makes a ton of revenue, that P minus epsilon, or that P plus epsilon will make a ton of revenue, because by raising the price even by a little bit, I might cause the number of people who are willing to buy the item to drop arbitrarily. On the other hand, it is the case that if I reduce the price by only a little bit, then it will have only a bounded effect on my revenue, right? Because remember, what's the expression for my revenue? What's the expression for the revenue that I get if I try to sell the item to everybody at some fixed price P? It's P times the number of people willing to buy the item at price P. The problem was the number of people willing to buy the item at some price P might like drop from everybody to 0 if I raise it by a little bit. But if I lower the price, the number of people willing to buy the item at that price can only increase, right? So if I lower the price by some epsilon, the number of people willing to buy the item at that price can only go up. In the worst case, it stays the same. And the price itself has gone down by a little bit. Okay, so I make a little bit less money on each sale, but I make at least as many sales. And the nice thing about this discrete grid of prices that includes every multiple of alpha between 0 and 1 is that no matter what the price, no matter what the optimal price was, there's always some price P prime in this discrete set, such that P prime is on the one hand less than the optimal price. So there's just as many people willing to buy at price P prime as there were willing to buy at price P, but it's not too much smaller. In particular, P prime is more than P minus alpha, because we have every multiple of alpha in this set. Okay, and so no matter what the optimal price was, P, I can pick a smaller price P prime in this set that is at least P minus alpha. At least as many people are going to be willing to buy the item at price P prime compared to price P. And on each of those sales, I will make at most alpha less than had I used the optimal price. Okay, and so my revenue is my loss in revenue by using this suboptimal price is at most alpha times n. Because in the worst case, everybody was willing to buy at price P. And so I've lost alpha per sale, and there were n sales. So in the worst case, I lose alpha times n, but not more than that. Does that make sense? And this is sort of going to drive the trade-off, right? The smaller we make alpha, the bigger the size of our number of experts, right? And we're going to pay for that in the error term of the polynomial weights algorithm. On the other hand, the smaller I make alpha, the closer the thing that the polynomial weights algorithm is able to compete with will be to the thing that I really want to compete with. Okay. Are there questions about these two observations? Okay. So we can combine these two guarantees, and we can plug them into the theorem governing the reward of the polynomial weights algorithm. Okay, so if we just use this alpha discretized set n, then what the polynomial weights algorithm guarantees is that the revenue that it obtains, the revenue of this truthful, dominant strategy truthful online auction, is at least the revenue of the best fixed price in hindsight, the profit benchmark we're trying to compete against, minus two things, okay? Minus the error term of the polynomial weights algorithm, 2 root n times log of the number of experts. Log of the number of experts in this case is just log of 1 over alpha. So as alpha goes to 0, this term will get bigger and bigger. And then minus alpha times n, which is the maximum difference between the revenue of the best price achievable by any of the experts in the polynomial weights algorithm and the revenue of the best price achievable period. The polynomial weights algorithm guarantees that we do as well as the best expert in our discrete set, and we want to compete with the best expert in this continuous set, and the difference between those two things is at most alpha n, and so we have to subtract off this alpha n term. But alpha is a parameter, right? Like alpha is something we get to choose, and so we can choose the value of alpha that makes cumulatively these two error terms as small as possible. And so you could, improve the constant by a little bit by choosing the exactly optimal value of alpha by trying to exactly equalize these two error terms. But, here's a very easy choice that gets within a factor of 1.5 the correct bound. So in particular, we could just choose alpha to be 1 over n, 1 over the number of bidders. Okay? Then both of these terms become simple, right? Alpha n becomes just 1, right? It's n times 1 over n. And this term becomes the square root of n log n, right? Because 1 over alpha, if alpha is 1 over n, it's just log n. Okay, and like for sure, whatever this thing is, square root of n log n, it is bigger than 1. So, what we get is this very simple expression for this particular choice of alpha, which is just that the revenue obtainable by the dominant strategy truthful auction we've derived, that's sort of driven by the polynomial weights algorithm under the hood, is at least the revenue of the best fixed price in hindsight, this sort of optimal revenue benchmark, minus some error term that scales like 3 root n log n. And again, if you chose alpha a little bit more carefully, you could make this 3 a little bit smaller, but the right answer would be somewhere between 2 and 3. Okay. And so let's think about this guarantee. Like, is this a good guarantee or not? And strictly speaking, this is actually like an incomparable guarantee to the 4 approximation we derived last time, right? Because a 4 approximation is multiplicative. But what we derived last time for the offline random sampling auction was that no matter what the benchmark value was, the optimal pricing, so long as the optimal pricing sold to at least 2 people, we would get at least a quarter of that revenue, even if the optimal revenue was teeny tiny, right? Like a multiplicative approximation means we don't care about the scale of opt. On the other hand, this is an additive approximation. And so it's incomparable because in particular, like if opt is smaller than root n log n, then this isn't promising us anything at all. On the other hand, this is actually a pretty good guarantee, right? Because what is the scale that we should think of opt as having? Opt is the optimal revenue we could get selling to n people where we have no constraint on the supply at all. So you would naturally expect that whatever opt is, our optimal revenue to selling to n people, it should be something that grows with n, right? Like I should have more money available in the market if I, like increase the size of the market. Maybe even, you'd think I double the revenue I can obtain if I double the size of the market. And so what this is saying is that rather than a 4 approximation, we are getting what is asymptotically a 1 approximation to the revenue of the best fixed benchmark, so long as opt, the sort of optimal revenue obtainable by the best fixed price when we sell to n bidders, is something that grows asymptotically faster than square root of n log n. Okay, like for example, if opt was growing linearly with the number of bidders, if our revenue was roughly, n over 100 or something, then this term would quickly become a low order term, right? Because root n grows a lot smaller than n. And this would be saying, as a multiplicative approximation, we would be approaching 1. We would be getting a sort of almost perfect approximation to the optimal revenue. And so this is like actually a pretty natural condition. Like, for example, suppose the bidders actually were drawn from some distribution. All we would need for opt to grow faster than root n log n is that there should be some constant probability so that bidder valuations are larger than log n over root n, right? Because of course we could charge this price, log n over root n, and if a constant fraction of the bidders were willing to buy at that price, then our revenue would be, on the order of n times this. So root n times log n, which is asymptotically bigger than root n times root log n. And if we were in this Bayesian setting that we considered a couple of lectures ago, where everyone had their valuation drawn from some distribution, then this would be true for every single distribution, so long as it didn't place all of its weight on 0, right? Because log n over root n is like a variable that goes to 0 the bigger I make n. Whereas if I have a fixed distribution, like, there's going to be like some particular value that shows up, with probability at least 1 over 100, like 0.01 or something. And so whatever that value is, like as I make n larger and larger, this condition will start to hold. And so like if buyer valuations are actually drawn from some fixed distribution, then I will find that my optimal revenue, like always does, grow linearly with n as I draw more and more people from the distribution. Okay, so this is actually a pretty good guarantee, because remember, we're competing with the revenue of the best fixed price. If people were drawn from a distribution and I knew what that was, then the revenue optimal auction would just be a fixed price, right? That I could derive from these virtual value functions. And this is saying, if we find ourselves in that setting, okay, even though we don't know what the distribution is, no matter what it is, we are getting asymptotically a perfect approximation to the optimal revenue. But now we didn't need to assume there was a distribution, and we didn't need to assume everyone was available up front. Okay, so that's it for today. I'm going to stop the recording, but I'll stick around for a few minutes in case there are any questions. Thanks, guys.